Hello guys, welcome to the Exam 3 review video. Before we start, similar disclaimer to the Exam 2 review video, this is a guide to help you study the review packet. That's the best way to study. Okay, other than that, I'm just going to jump right into it. We started off Unit 7 with 7.1 and 7.2, which was about angle measure. So remember that an angle is made by two rays, which I've drawn here, together with a shared vertex. They meet together at this point right here. We can slap a circle centered on this vertex, and these two rays will subtend, or in other words, trace out a proportion of this circumference. So in this case, it's traced out like an eighth of the circumference, right? Since we can fit 8 of them around here. This proportion is how we define an angle. We have two units that we can use, and both of them sort of give us a measure, right? So radians, which is the most important one, you should really think about these and really know these well. 1 radian is the angle which subtends exactly 1 radius length. If you look up radians intro GIF on YouTube, and I think I'll have it linked in the description, it's a really good visual aid for what exactly a radian is. Since the circumference is 2 pi times our radius, or 2 pi times as large as a radius, we can fit 2 pi radius lengths along the circle, or in other words, 1 full rotation around the circle is 2 pi radians. Now, you should be able to give this just as easily as you can give me 360 degrees, okay? So practice remembering a full rotation in radians. Try even practicing some of the common calculations. So we know that a half of a rotation is half of 2 pi. So this right here is pi. Oh, that's not a pi, that's an h. That's pi. Okay, same with degrees. 1 degree is kind of defined weirdly. It's defined as an angle which subtends exactly 1/360th of the circumference. Okay, on to converting. If you are given units in one measure and you need to find it in the other, first of all, figure out what proportion of a full rotation it is, and then use this to find the angle in the other units, okay? So I have 2 examples down here. Try them on your own first, but I'm going to go straight into them. So pi over 3 radians is exactly pi over 3 divided by 2 pi proportions of a full rotation, right? I'm going to calculate this out. Our pi's are going to, so we have pi over 3, and then we're dividing by 2 pi. So this is times 1 over 2 pi. Our pi's are going to cancel out, and we're left with 1/6 of a full rotation. And now to convert this to degrees, we know that a full rotation in degrees is 360. And so 360 divided by 6, that's going to give us 60 degrees. Okay. Next is converting 50 degrees to radians. Well, we know that 360 degrees is in a full rotation. So this is the proportion of a full rotation we get. We put that in our calculator. We can find a simplified fraction as 5 over 36, right? We just divide by 10. And then to find it in, so this is 5 over 36 of a full rotation. Well, we know that a full rotation in radians is 2 pi. So this is 10 pi divided by 36 radians, or 5 pi divided by 18 radians, if we simplify. All right. On to arc length and radius. This was 5.2, or 7.2, excuse me. So because 1 radian subtends exactly 1 radius length on a circle, then if we have 2 radians, that's going to swipe out 2 radius lengths. If we have 3 radians, that'll swipe out 3 radius lengths. And in general, an angle of theta radians will subtend theta radius lengths along our circle. In other words, arc length, which we call S, is just going to be r times as large as our angle. Okay? So I'm going to give us 2 examples here. Again, pause and try on your own. This first one, you are traveling on a circular track, and you make an angle of 1.8 radians. I want to know what distance we've traveled along the track in feet. So go ahead and try that yourself. Okay? Well, our angle is 1.8 radians. And we know that 1 radian traces out 1 radius. So this is going to be multiplied by our radius, which is 12 feet. And so we're going to get 1.8 times 12. which is 21.6 feet. All right. Similarly, for this next one, I want to know, with the same context, what angle have you made if you've traveled 55 feet? How many radius lengths have you traveled? Will give us the angle. So if the radius is 12 feet, then we've traveled 55 divided by 12 radius lengths. We put this in our calculators. 55 divided by 12 is going to give us 4.583. And that's our measure in radians, right? Our radian measure is asking us how many radius lengths have we subtended on our circle. And if we've subtended 55 feet, well, that's 4.58 radius lengths. So 4.58 radians. All right. On to 7.3 and 7.4. This was representing circular motion. So this is when we introduce the concept of sine and cosine. So we're always going to take a circle with an initial ray, so starting ray, pointed in the 3 o'clock position. We call that the initial ray. And a terminal ray rotating counterclockwise, so up this way. We call the point on the terminal ray intersecting with the circle the terminal point, which I've marked here. Okay. With this, we have two quantities that are of note. We have its horizontal distance to the right, which I've represented by this blue arrow, and its vertical distance above, which I've represented with this pink arrow. Sine and cosine are both functions that take in angle counterclockwise from 3 o'clock in radians. And sine is going to spit out the distance above measured in radius length. So it's going to be a proportion of a radius. If sine of theta equals 0.9, well, then that means that our vertical arrow is 0.9 times as large as our radius. Similarly, for cosine, our output is going to be a proportion of the radius length that our point is to the right. Now, if sine is negative, that means we're below. If cosine is negative, that means we're to the left. So an example here, I want to know the coordinate x comma y of this terminal point here. And so pause, take some time to find out, and then come back. I want this in units, so not in radius lengths, in units. Okay. Well, in radius lengths, it's going to be given by cosine of our angle, which is 2.8, comma sine of 2.8. And this is in radius lengths. Well, what is my radius length? My radius length is 12.3. So my point is going to land at 12.3 cosine of 2.8 and 12.3 sine of 2.8, right? We stretch it out by that radius factor. Okay, another example. On this circle, figure out the value of sine of theta and cosine of theta. Again, pause and try again. Well, not my iPad rotating. Well, sine of theta is going to be how far above the circle I am in radius lengths. That's going to be related to my y-coordinate. My y-coordinate is negative 11.91. And my radius here is 13. Radius is 13. So my proportion is that divided by 13. Similarly, my cosine of theta is going to be this proportion to the right in terms of radius lengths. And so it's going to be negative 5.21 because we're to the left. Excuse me. And again, we need that in radius length, so we're going to divide by 13. Challenge for you. Find theta using any method you want. All right. Now we're on to transformations of sine and cosine. Remember, sine and cosine are going to take in an angle. We have to input an angle. We cannot put time into our trig functions. We cannot put distance into our trig functions. We need an angle, okay? Sometimes our problems will be modeled in terms of time, and we're going to need to figure out angle in terms of time. Okay. Here was a classic example that you probably did in class. I am spinning a ball on a 2.3 foot long string at a constant rate of 2 radians per second, keeping my hand at the center of the circle, traced out by the ball. I start at the 3 o'clock position and I travel counterclockwise. I want to find an expression for the ball's height above my hand in feet in terms of seconds elapsed since starting to spin, which I'll call t. This is a lot, and so you might get overwhelmed by this, but let me just point out some things. Keeping my hand at the center of the circle, traced out by the ball, starting at the 3 o'clock position, traveling counterclockwise. This whole thing right here, all of this is just set up to tell us it's normal, right? We're starting at 3 o'clock, all good. We're traveling counterclockwise, nice. And something is staying centered at this circle, okay? So we can kind of ignore this. It doesn't really matter. Okay, this 2 foot long string is going to correspond to my radius, right? This constant rate of 2 radians per second is my rotational speed. And using those two things, I can find it pretty easily. I need to find the ball's height above my hand, which means I'm going to be using sine, right? So sine deals with vertical distance, so height. Cosine deals with left and right distance. So drawing a picture is always really helpful, right? I'm starting my ball at this 3 o'clock position here. So here's my initial ray. And then I'm going to rotate it counterclockwise to form this angle here. And I want to find my vertical distance above my hand. Okay. Well, this pink arrow is going to be sine of theta times as large as my radius. And now we have to figure out what my angle is in terms of time. So we're traveling at 2 radians per second, right? So I'm going to make a table here. After 1 second, our angle now is 2 radians. After 2 seconds, our angle here is 4 radians. What if I put something weird like 11.2? Well, my angle is just going to double, so 22.4 radians. And in general, if I have a value of t over here, it's going to be 2 times t, okay? So in total, my angle is given by 2t, so theta is 2t. Now we have an angle. We can plug that into sine. So this pink arrow right here, the length of this pink arrow is given by r times sine of theta. And our angle is going to be given by 2t. And this is our formula for the height in terms of time. All right. 2 other things of note are period and rotational speed. Okay. So here's number 8 and number 5 from your workbooks. Number 8 is saying, Jose takes 20 seconds to complete revolution, and we need to determine the speed of the ball in radius length per second. And question 5 is, I've modified it a little bit. Jose twirls the ball so that it travels 1.5 radius lengths per second along its circular path. And we want to know over what time interval does the ball complete 1 revolution. For problems with periods and speeds, remember, rotational speed is given by our change in angle over change in time, right? If I travel 2 radians per minute, well, that's my speed, is 2 radians, that's my change in angle, every 1 minute, okay? We always know that there are 2 pi radians in a full rotation, and again, practice this. If we're given the speed, k, we know that the speed is 2 pi divided by the period, so we can solve for the period. If I'm given the period, then I know that speed is going to be just 2 pi divided by my period. This is my change in angle. In 1 rotation, I changed by 2 pi. And the time it took, well, that was my change in time, which was 1 period. Okay. So with that in mind, let's try to solve these. So pause it, try to figure it out yourself. But for this one, my change in angle over a full rotation is 2 pi. That's 1 revolution. And my change in time is 20 seconds. And let me be careful here and put radians, right? That's our measure. Got to put units. And so my speed is just my change in angle over change in time, which is 2 pi divided by 20 radians per second. Boom. For number 5, if the ball is traveling 1.5 radius lengths per second, well, then that means 1.5 radius lengths per second is equal to my change in angle, so 2 pi, divided by my period, right? In one period, I'm going to travel 2 pi. That's going to give me my speed. So solving for p, I like to use something that I call my little hat trick. We're trying to solve for p, but p has a hat on. Just give it to the other side. P is going to equal 2 pi divided by 1.5, right? We just gave 1.5 p's hat. We just took this hat off of p and put it on 1.5. I like to do that. You can also cross multiply if you like, but this is the method that I like to use. And so this would be our period. Okay. Remember, for modeling problems, speed goes into sine or cosine, not period. Okay. So thinking back to up here, our period, well, since we're going at 2 times the speed, our period is pi. It'll take pi minutes for that full rotation, or excuse me, pi seconds for that full rotation, since we're traveling twice as fast. However, we never put pi into our sine. We put 2. So our speed goes in here, okay? So on a 7.6, this was the Ferris wheel problem. And I want to take some time, go through this again in your workbooks. It's a really, really good problem, and try to really understand it. So we have a Ferris wheel with a 52-foot radius, a horizontal diameter located 58 feet above the ground. I think that you have this all filled out in your workbooks already, so don't worry about that. I just wanted to find a function about this. I wanted to find a function for, excuse me, the distance in feet of the Ferris wheel bucket above the ground in terms of the number of minutes since the Ferris wheel began rotating, starting at the 3 o'clock position and rotating at this constant rate of 1/4 of a radian per minute. Okay. My first thing I like to do is look at this 1/4 radian per minute. That tells me that my angle is just 1/4 times how much time has passed. Okay. My second thing is, what is my radius? My radius is equal to 52 feet. So I know that 52 times sine of 1/4 t, well, this is going to give me, I'm going to highlight this green. This part is going to give me my vertical distance above the center of the Ferris wheel, right? So if I draw my picture here, we have our Ferris wheel. It's 58 feet above the ground. That's an 8, 58 feet. And its radius is 52 feet. Well, again, if I make an angle from 3 o'clock, my height here, excuse me, if I can draw it, this pink arrow here is 52, or our radius times as long as sine of theta. And again, our angle is just 1/4 t, right? So this is going to give us our height above the center of the circle. Well, how high is the center of the circle above the ground? We're just going to add this 58 right here. And so this would be our function. So again, if we had something like h of t equals 52 sine 2t plus 58, this would represent the same situation, right? Our radius hasn't changed. Our vertical distance of this Ferris wheel above the ground hasn't changed, but we're now spinning 8 times as fast. We're spinning at 2 radians per minute instead of 1/4 of a radian per minute. Remember, go back to this problem, use it to hopefully help you with the exam review packet. This one is really good. And if you can get this one down, then it shows you really understand our modeling of these functions. Okay. Taking it one step further to 7.7, we might start somewhere different from 3 o'clock. And we still need to be able to figure out our functions, okay? So real quick right here. What if I started at 12 o'clock, right? And I make an angle theta, which I've labeled yellow here, from this 12 o'clock position. Remember that sine and cosine are always going to take angles from our 3 o'clock position. So what we're really interested in is finding this measure of alpha, right? To model this function, we would need to find the angle from 3 o'clock, which is going to be something plus theta, okay? What angle takes me from 3 o'clock to 12 o'clock? What is this blue angle right here? Try to answer that. Use a piece of scratch paper and figure that out. What proportion of a full rotation is this, and then use that to find the angle measure in radians. This right here is a measure of pi over 2. Or in other words, my angle from 3 o'clock is just pi halves plus theta, okay? Does that make sense? I hope that that makes sense. And I hope that you're looking at this and this diagram makes a little bit of sense to me. But remember for sine and cosine that we always want to give angles starting from 3 o'clock and going counterclockwise. So if we start at 12 o'clock, if this is where I start, well, then I need to compensate by that by telling myself, okay, how do I get from 3 o'clock to that in that new starting position? And that's what we're going to add to our angles. Okay. So an example, this was from 7.7. Janine is going to board a Ferris wheel from the bottom, so the 6 o'clock position. I'm going to draw it out, and I hope that you guys draw it out too. It's going to then travel at a constant rotational speed of 0.9 radians per minute counterclockwise. The Ferris wheel has a radius of 35 feet, so I'm going to write that here, 35 feet, and its center is 40 feet above the ground. We want an expression for her height t minutes after the Ferris wheel begins to move. So her height from the ground. Okay. Now she's going to start down here and she's going to travel counterclockwise. So if she makes this angle, which I'm going to call theta, what angle from 3 o'clock has she made? Or in other words, I'm going to draw this angle here. What is this blue angle that we have to add to find her angle from 3 o'clock? Pause and try to figure out for yourself. There's two answers that you could give here, okay? The first one is the one that I would probably use, and it's knowing that we're figuring out that this is 3 pi divided by 2, right? This angle measure is 3/4 of a full rotation, so 3 pi over 2. So whatever angle we make from 6 o'clock counterclockwise, this yellow part right here, right? We're going to have to add that to 3 pi over 2 in order to use in sine or cosine, right? Okay. So I'm going to call, again, this full thing alpha, right? I'm interested in this angle from 3 o'clock. So alpha is given by 3 pi over 2 plus theta. You could have also had negative pi over 2 plus theta, whichever floats your boat, whichever you like better. But either way, we have an expression for this total angle given by whatever angle we've made from 6 o'clock, okay? And since we're traveling at 0.9 radians per minute, well, this means that this is just going to equal 3 pi over 2 plus 0.9 times t, right? After 1 second, we're 9/10 of a radian from this position. After 2 seconds, we're 1.8 radians away. After 3 seconds, we're 3 times 0.9 radians from this 6 o'clock position. And so we add that to 3 pi over 2. So this is what we're going to put into sine or cosine. Okay. We want an expression for her height, so we're going to use sine. And we're following the exact same rules as before. So 35, our radius, times sine. And we want our angle in terms of time, so 3 pi over 2 plus 0.9 t. And then the Ferris wheel is 40 feet above the ground. So this is an expression for her, her height. Really look back at 7.7 and try to make sense of this. It's all about, it's exactly the same thing that we did before. If you can do this, you can do 7.7. All that it requires is that we think about our starting position. So this starting position at 12 is pi halves of a rotation away. Pi halves radians of a rotation away. And similarly down here, the 6 o'clock position is 3 pi over 2 away from that 3 o'clock position. So just keeping those in mind. Okay. We're going to move on to graphs. And my strategy for the graphs is always this. So my midline is going to be my halfway value between my minimum and maximum values. So I'm going to add my max and my min together. And min could be negative. I could do 5 plus -2, right? If my graph looks something like this, here's 5 Here's -2. If I had something like this, then I would take 5 plus -2 and I would divide by 2 to find my midline, right? So keep the sign, but we're adding it. So plus -2, or in other words, 5 minus 2. I like to write it like this because it makes more sense. My max plus my min. My min just happens to be negative. My amplitude is how far the max and min are from the midline, or half the distance between the min or max, whichever you want to use. And our period is the input change it takes to make one full cycle. You can also just take the input change between two max values or two minimum values. And I'm going to go over that here. Pause and try for yourself. And all of 33, so this is just part C, but all of 33 is really good on the exam review packet. We want to find the function for this graph. So try yourself, pause it, and then come back. Well, first of all, I'm going to calculate my midline. So my max value is 2. And my minimum value is -4. So my midline is going to be, I'm going to switch from blue, 2 plus -4 divided by 2. Or in other words, 2 minus 4 divided by 2, which gives you -1. I'm going to draw my midline here. And you can see it nicely splits our function in half, okay? Well, now my amplitude is going to be how far above or below my midline I go. So I'm starting at -1 here. Well, my max and my min are both 3 units away. So my amplitude is 3. You could have also done 2 minus -4 divided by 2, which is 2 plus 4 divided by 2, or 3. But I like this better because it's more visual. I can see it. And finally, our period is going to be how long it takes to make that full rotation. Well, there's two ways I can do this. I can trace out one full rotation here, right? So going from my 2 minimum points, the distance between these guys in my input land is pi. So my period is pi. You could have also found this using 2 maxima. Anytime you just count a full cycle, you have the period. And so my period here is pi. Now I need to find my speed. That's what I put into my sine and cosine function. So first of all, we need to know whether this is going to be sine or cosine and whether it's going to be negative or positive. So for this one, what I like to do is I'm going to draw this here. I should have drawn this here. So sine looks like this. It starts at our midline and goes up, right? So this is the regular value for sine. And for cosine, it starts at a maximum value and then kind of starts wiggling around, right? So it starts at a maximum. So looking at this, do we start at a max or a min, cosine, or do we start at our midline? That's sine. So right here is where we start when our input is 0. So we're going to have to use cosine here since we start at a minimum value. But cosine usually starts at a maximum value, so we know we're going to need to flip this in a negative cosine of theta, which looks like this. Okay. I hope that's at least a little bit clear, right? We're going to use cosine because we're starting at our maximum or minimums, and we're not starting right here in our midline. Now that we know our period, we need to know our speed. So remember, our speed is our change in angle over change in time. Well, our change in angle in a full rotation is 2 pi, and our period is pi. So our speed is going to be twice as fast. And so putting that all together, my amplitude 3 goes out front. We're going to use cosine, and it's going to be negative. So 3 times negative cosine. I'm going to bring these together. This is -3 cosine of 2t, right? Or I guess in terms of x, so 2x, because my speed goes in there. And then my midline is -1, so I subtract 1. And here is our completed function. Awesome. So finally moving on, or not finally, almost finally, moving on to the tangent function. So just like sine and cosine, tangent is going to take an angle counterclockwise from 3 o'clock in radians, okay? What is going to output us is the slope of that terminal ray. Since slope is just given by the change in y over change in x, I know that tangent of theta is sine of theta divided by cosine of theta. Okay. An example Find the slope. If x equals 2, what is y? Okay. So, first of all, our slope is pretty easy. It's just given by our tangent of that angle from 3 o'clock, which is 3. So tangent of 3, if you put that in your calculators, you're going to get negative 0.143. Okay, well, this is our change in y divided by our change in x, right? Well, if this coordinate right here is 2 comma y, well, then that means my slope is y divided by, or excuse me, not 2 comma y. I'm gonna fix this. I made this wrong in the problem. If x equals negative 2, excuse me, what is y? Well, if this point is negative 2 comma y, that means that my slope, which is my change in y over change in x, that's going to be my change in y divided by negative 2, my y divided by negative 2, right? That's my slope. And that's going to have to equal negative 0.143, which means that my y value is going to be negative 2 times negative 0.143. And if we put that in our calculator, we get 0.285. Lovely. All right. As an example, I also want to label on the quadrants whether it's positive or negative. So this first one is for sine, second one is for cosine, and the last one is for tangent. And then I'll show you my trick to doing this. I'm going to move this out here, move this out here, just so we know that this is quadrant 1, 2, 3, 4. Okay. So for sine, I'm happy whenever I'm above the circle. So it's positive here. And it's going to be sad whenever it's below the circle. It's negative here. Cosine is left, right. So it's sad when it's to the left, happy when it's to the right, positive to the right. For tangent, what I like to do is draw 2 lines going through the circle, okay? Since tangent is the slope, which one of these lines has positive slope? This one right here. So tangent is positive in the first and third quadrants, and negative here. I like to draw this out because I don't have to think very much. I can draw my lines and I know that tangent is slope. And so it's going to be negative here and here and positive, negative here and here, positive here and here. And it also reminds me how to calculate multiple values for inverse tangent. Not going to get there yet, but almost. And yeah, so just making sure you can reason on all of these for the exam. Finally, with 7.9, almost finally, second to last one. This was negative angles and coterminal angles. So by convention, we say that clockwise angles are positive and, counterclockwise angles are positive and clockwise angles are negative. So this blue angle right here, just like what we've been doing for forever, it's a value of theta. If we go clockwise instead, that's negative theta. Okay. We call 2 angles coterminal if there are some number of full rotations away from each other. Or in other words, their terminal rays lie on the same point. If I was physically here with you guys, I would be rotating myself to demonstrate, but you'll have to think of a picture in your head. So an example is find 2 coterminal angles for 3 pi over 4, one negative and one positive. Try that for yourself. All right. So I'm going to find my positive one first. So I'm just going to add 2 pi. I'm going to add a full rotation to get back to the same place. So this is 3 pi over 4 plus, and I want to have the same denominator, right? So this is going to be 8 pi over 4. And so this is going to be 11 pi divided by 4. And my negative one is going to be 3 pi over 4 minus 2 pi. Well, then that's going to be 3 pi over 4 minus 4 pi over 4, or excuse me, minus 8 pi over 4, which is equal to negative 5 pi over 4. And these are my 2 angles. If you guys get caught up with pi, just take it out. So 3 pi over 4 plus 2 pi. Well, this is the same as 3/4 plus 2 all times pi. Do this out together. So 3/4 plus 8/4. So 11/4. And we're keeping this pi outside. So this is 11 over 4 pi. It's the same thing we did here, but you can take the pi out and not have to worry until the end. Right, on to our very last topic. This is the inverse trigonometric functions. So remember this not this diagram, but please remember your inputs and outputs for sine, cosine, and tangent. For sine, cosine, and tangent, the input is always going to be angle counterclockwise from 3 o'clock in radians, very specific. Sine is going to output vertical distance above and radius lengths. Cosine is going to output horizontal distance to the right in radius lengths. And tangent is going to output slope. What this means is arcsine is going to take in distance above and tell us what angle would give us such a point. Now remember, the distance above is in radius lengths. So if we have a circle like this of radius, let's say 5, so this is the point 50, and I give you the point 3, 4, then sine of theta is 4/5. It's not 4. It is not 4. It is 4/5. It's that proportion of the radius. Be careful. Same for arc cosine and arc tangent. I may share these notes below, and you might be able to see this and just download it. And real quick, we have to restrict the domains of sine and cosine and tangent when we're doing these inverse functions. Why do we do that? Well, let's take a look. If I told you, I'm going to go over here, that I'm on a Ferris wheel, okay? And I told you, help me. I'm going to draw our buckets, and my class saw this, so you guys are going to see it again. But if I told you, help me, I'm stuck, I'm in the blue one, get me out, you'd be like, that doesn't help, there's a billion blue ones. Okay. Functions have to give us one value, right? So this would be like asking you to give me an output for blue, right? Like I just can't tell you which one I'm in. Now, if I told you that my vertical distance is half of the radius, well, I could be either of these two, right? Right? Both of these are halfway above. They have the same y coordinate, right? But that still doesn't help you because now there's 2 points, okay? So like right on this diagram, it's what it would look like. If I told you sine of theta was 0.5, you could have either of these 2 points. You wouldn't have enough to find that angle. So what sine of inverse does is it only looks at the right half of the circle. It's only going to give you this one. You're going to have to figure out what this other one is, okay? Same for cosine. If I told you my cosine was something, well, what's another point with the same cosine? It'll have the same horizontal distance. So it'll be one of these 2 points. You're going to have to find the other angle. It will only give you the one on top. So inverse sine is only going to give you an angle on the right. Inverse cosine is only going to give you an angle on the top. And inverse tangent is only going to give you an angle on the right side. So just keep these in mind when you're solving. Really good practice for all of these is 26, 27, 28, and 29. And remember, arcsine and arctangent only care about the right side, while arccosine only cares about the top, and you will need to find the other point. Let me go to this real quick. What I taught my students a little bit was that for all of these, so this was my example that I did in class, to demonstrate on the following circles, how we can estimate this value for theta, right? Well, if cosine of theta equals negative 0.5, I can put cosine inverse of negative 0.75 into my calculator to give me one of these angles right here. And it ends up giving me this one right here. But I need to find both of these. There's 2 points, right? So I need to somehow figure out that other one. But again, the general thing for all of these, draw a circle, draw what it means for cosine of theta or sine of theta or tangent of theta to equal whatever you're given. And then there's always going to be 2 points that satisfy that. So find both of them. Take your arc cosine, your arc sine, your arc tangent to find one of the angles, and then use your picture to find the other. So it depends on whether you have arc sine, arc tangent, or arc cosine. Again, look in your workbooks for this. But yeah, that is all I have for you guys. Good luck. Do that review packet. And yeah, you guys are going to do amazing. Please make sure to get some good rest, eat some food, drink some water, But yeah, have a great weekend and good luck on your exam.